We're going to talk now about some of the relationships that were noticed by several famous scientists in terms of the relationship between the measurable quantities for gases. So, for instance, pressure and volume, or volume and temperature, and I think in another presentation I'll talk about pressure and temperature. So we're going to talk about Boyle's law here, and this is my kind of analogy as to what's going on with Boyle's law. So if I pull a syringe plunger back and fill the syringe with air and then place a stopper over the tip of that syringe and then push in on the syringe, I expect that you can guess what's happening to that gas that I've just compressed there. So as I pushed in, I decreased the volume of the gas, but that corresponded to an increase in the pressure of the gas. So the volume decreased, the pressure increased. So that's an indication that this is or what we call an inverse relationship. So the pressure is related to 1 over the volume, and I'm using an arbitrary constant here, K, to hold the proportionality. So I could rearrange that by moving the V over to the other side by multiplying both sides by V, and I get P times V is equal to K, and as long as I have the same gas trapped here at the same temperature, then any relationship between P and V should be equivalent to one another. So P1 times V1 is equal to K, the same for P2 and V2, P3 and V3. So I'm just going to say that they're equal to the same constant, and two things that are equal to the same constant are equal to each other, and that's what Boyle's law says. So I'll never ask you to recite Boyle's law, but I might expect you to understand what the volume and pressure relationship is for gases. So we can put that to work for us. So I'm going to use another syringe example here. I've collected 25 milliliters of gas in my syringe. It was open to the atmosphere before I put my stopper on there, so I can assume that it is at whatever the atmospheric pressure is, and I used an ideal atmosphere here, so I must have been pretty close to sea level when I did this. And I want to know what the volume of the gas would be if the pressure was 975 millimeters of mercury. I know 760 is 1 atmosphere, so this is a little bit more than 1 atmosphere of pressure. And what we want to do first with gas law problems is tabulate the data. So my starting pressure, P1, was 1 atmosphere, V1 was 25 milliliters. I started with P2 at 975 millimeters of mercury and then converted it to atmospheres, so 1.28 atmospheres here. And I don't know what the volume 2 is, but that's what I'm going to solve for. I've got Boyle's law equation here. P1 V1 is equal to P2 V2. I can plug the numbers in their appropriate spot. So that's the beauty of having a table, is it helps you get the numbers in the right spot. So 1 atmosphere times 25 milliliters is equal to 1.2 atmospheres times whatever V2 is. And in order to get V2 all by itself, I'm going to divide both sides by 1.28 atmospheres. And they're going to go away from the right-hand side, and the units go away as well on the left-hand side. And if I just do the math, I get 19.5 milliliters. And that makes sense that the pressure went up, and like we saw on the previous animation, that when the volume went down, the pressure goes up. So that number makes sense to me. Okay, Charles' law was looking at, was looking at the relationship between volume and temperature. Ultimately, he was interested in whether there was a temperature out there where the volume of a gas would go to 0. So essentially, he was seeking out what the value of absolute 0 is, and for his work, he was awarded the title of Lord Kelvin. So it's kind of interesting that Charles and Kelvin are one and the same here. So my animation here is that I've got a balloon. I filled it up on a nice warm sunny day, and I go over to Hy-Vee and walk into the cooler and observe what happens to my balloon. it wouldn't necessarily be this dramatic, but you would see that the volume of the balloon would decrease, and you've probably seen this with a basketball that you'd left out in the garage from summer to winter, or maybe you've noticed that the tires on your bike or your car seem like they're less full when the temperature goes down drastically. So these are going in the same direction. The temperature decreased and the volume decreased, so it's a direct proportion. So in this case, volume is proportional to temperature. So I got V is equal to K times T here, and I've got that K2 is just a proportionality constant. I can move the T over to the other side and get the K by itself, so V over T is equal to K. So V1 over T1 is equal to K2, and any ratio of volume and temperature for a confined gas at a fixed pressure is going to show this relationship. And if they're both equal to the same constant, they're equal to each other. So V1 over T1 is equal to V2 over T2. So let's do a little work with this Charles's law. Okay, I've got a balloon, and I filled it up to 2 liters of volume at 25 degrees Celsius, and I want to know what the temperature would be if the balloon had a volume of 3 liters. So like before, tabulate your data first. So the 2 liters is my starting point, so I'm going to call that V1. T1 was the 25 degrees Celsius, and I needed to turn that into Kelvin. Remember, I'd mentioned in an earlier presentation that you have to work in Kelvin. My final volume was 3 liters, and I just don't know what that temperature is. So I've got all of my data tabulated. All I need is my equation. V1 over T1 is equal to V2 over T2. I just plug and chug. I put the numbers where they correspond to on my table, and I've got T2 in the denominator. I remember when I was taking algebra, there was nothing more frightening than seeing an unknown variable in the denominator, but there's a quick solution to this, and some of you may recall that we can cross multiply. So when I cross multiply, I get 2 liters times T2 is equal to 3 liters times 298. So I want to get T2 by itself, so if I divide both sides by 2 liters, I should be in the clear. So according to my calculations, I got 450 Kelvin as the temperature where the volume would be 3 liters, or 170 degrees Celsius. So it isn't like walking into the cooler at high V. This is like walking into an oven here. So apparently I put my balloon in the oven to make it a volume of 3 liters.